Some stars are born to burn quietly for 10 billion years, and some are born to die. A massive star is one that begins its life with more than about 8 times the mass of our Sun, and that threshold is not arbitrary. It is the dividing line above which a star can push its nuclear burning all the way to iron and then collapse, rather than settling gently into old age as a white dwarf. Such stars are rare, because for every giant there are hundreds of ordinary suns. They utterly dominate the life of a galaxy. They pour out most of its light, they stir its gas with their winds and their deaths, and they forge and scatter nearly all of the heavy elements from which planets and people are made. To follow one of these stars from birth to detonation is to watch the universe manufacture the ingredients of worlds, and to witness the single most energetic ending that ordinary matter can come to. This is the story of how the largest stars live fast and die in fire. On the main sequence, a massive star fuses hydrogen into helium not by the slow proton chain that warms the Sun, but through the carbon-nitrogen-oxygen cycle, in which those heavier nuclei act as catalysts. That reaction is fantastically sensitive to temperature, rising almost as the 16th power of it, so in the fierce heat of a massive core the energy is generated in a tiny central region that boils with convection. The consequences are extreme. A star's brightness climbs steeply with its mass, roughly as mass to the 3.5 power, so a star of 25 solar masses shines some 80,000 times more brilliantly than the Sun. Burning so prodigally, it exhausts its hydrogen in only a few million years, where the Sun will last 10 billion, and it bleeds. Radiation pours off these stars so hard that it drives powerful winds, stripping away their outer layers over their lifetimes, and in the most luminous cases, approaching the Eddington limit where light itself nearly overcomes gravity. When the hydrogen in the core finally runs out, the star does not stop, it transforms. The inert helium core, no longer generating heat, contracts and grows hotter, while a shell of hydrogen ignites around it. The outer envelope, meanwhile, swells enormously and cools, and the star balloons into a red supergiant, one of the largest objects in the cosmos, so vast it could swallow the orbit of Jupiter. Deep inside, the contracting helium core soon reaches 100 million degrees, hot enough to ignite a new fuel. Helium begins to fuse into carbon and oxygen, and the star embarks on a series of ever briefer, ever hotter burning stages. Each one will build a new layer, and each will bring the star a step closer to its doom, laying down, shell by shell, the strange architecture of its final days. What forms is one of nature's most remarkable structures, often likened to an onion. Each fuel ignites in the core, burns out, and then continues burning in a shell around the newly contracted center, which grows hot enough to ignite the next fuel in turn. So the dying star comes to hold nested shells, hydrogen at the surface, then helium, then carbon, then neon, then oxygen, then silicon, wrapped around a growing core of iron. The pace is staggering in its acceleration. A star of around 25 solar masses burns hydrogen for some 7 million years, but helium for only about 700,000. Carbon burning lasts a mere 600 years. Neon burning takes about 1 year, oxygen burning roughly 6 months, and the final silicon burning is over in about a single day. In the span of one Earth day, the star races through the last of the fuel it has any hope of using. 2 facts drive that headlong rush. First, each successive fuel yields less energy than the one before, because the star is climbing an ever shallower part of the nuclear binding energy curve as it approaches iron. Fusing hydrogen to helium releases about 7 million electron volts per nucleon, the richest step of all. The later stages give up only a fraction of that, so more fuel must be consumed each second just to hold the star up. Second, and decisively, once the core passes about 500 million degrees, it begins to hemorrhage energy as neutrinos. Collisions in the searing plasma create neutrino-antineutrino pairs that stream straight out of the star at nearly the speed of light, stealing energy far faster than light itself could carry it away. By the silicon burning stage, the core is radiating vastly more power in neutrinos than in light, and it must burn furiously simply to replace what the neutrinos steal. All the while the surface shines on serenely, an ordinary-looking supergiant, oblivious to the frantic countdown within. Then the star builds the one thing it cannot burn. Iron and its neighbors sit at the very peak of the binding energy curve, the most tightly bound nuclei in existence, at about 8.8 million electron volts per nucleon. Fusion only releases energy when it moves toward that peak. To fuse iron into anything heavier would absorb energy rather than release it. So an iron core is an ash with no further fire in it. it is held up, not by heat but by electron degeneracy pressure, the same quantum stubbornness that supports a white dwarf, and like a white dwarf it has an absolute mass limit it can bear, the Chandrasekhar mass, near 1.4 times the mass of the Sun. As the silicon shell above keeps raining fresh iron down onto it, the core creeps toward that limit, a dead weight growing heavier by the second, approaching the moment when its own gravity will win. The end comes with terrifying speed. As the iron core is squeezed, two things happen that both steal away its support. Electrons are crushed onto protons inside the nuclei, turning them into neutrons and releasing yet more neutrinos, and each captured electron is one fewer particle holding the core up. At the same time, the core is so hot that gamma rays begin to shatter the iron nuclei back into helium and free particles, a reaction that drinks in energy and saps the pressure further. Robbed of support at the very instant it needs it most, the core can no longer hold, and it implodes almost in free fall. An object larger than the Earth collapses to the size of a city in a fraction of a second, the inner regions falling inward at nearly a quarter of the speed of light. A simple calculation of the freefall time gives only a few tens of milliseconds, less than the blink of an eye, less than a single beat of a human heart. The collapse is halted with equal violence. When the innermost core reaches the density of an atomic nucleus, some 300 trillion times the density of water, the strong nuclear force abruptly turns hard and resistant, and the equation of state stiffens like a wall. The infalling inner core rebounds, and that rebound launches a colossal shock wave outward into the still collapsing material above. Left behind at the center is a proto-neutron star, a searing ball of neutrons only a few tens of kilometers across. And the energy released is almost beyond comprehension. The collapse liberates gravitational binding energy of around 3 times 10 to the 53rd ergs, roughly a tenth of the entire rest mass energy of the neutron star. But here is the astonishing part. About 99% of that titanic energy escapes silently as neutrinos over some 10 seconds. Only about 1% goes into the visible explosion, and a mere 100th of 1% into light. A supernova is, at its heart, a neutrino event that merely happens to be visible. That fact creates the central puzzle of supernova theory, because the bounce shock by itself fails. As it plows outward it spends, its energy smashing the iron nuclei in its path and radiating neutrinos, and within milliseconds it stalls, hanging stationary while matter continues to rain down through it onto the proto-neutron star. What revives it is the neutrino flood. The proto-neutron star is so hot that it radiates neutrinos in unimaginable numbers, and a small fraction of them are reabsorbed in the layer just beneath the stalled shock, depositing their energy and building up pressure. This delayed neutrino heating mechanism, worked out by Hans Bethe and James Wilson in the 1980s, is helped enormously by violent churning. Large-scale convection and a sloshing instability of the shock break the symmetry and keep matter bathing in neutrinos longer. Simple spherical models often refuse to explode, while modern three-dimensional simulations increasingly succeed, though predicting exactly which stars explode remains a genuine frontier. That same lopsidedness kicks many newborn neutron stars off across the galaxy at hundreds of kilometers per second. When the explosion finally tears the star apart, astronomers classify what they see by its light, using a scheme older than the physics behind it. In 1941, Rudolf Minkowski split supernova by a single question: does the spectrum show hydrogen? Those with hydrogen he called type 2, those without type 1. We now know the deep irony of that scheme, for it does not track how the star died. A massive star that keeps its hydrogen envelope explodes as a hydrogen-rich type 2. One whose winds or a binary companion have stripped that envelope shows helium instead and is called type 1b, and one stripped of helium-2 is a type 1c, but all three are the same core collapse underneath. The genuine outsider is type 1a, which despite its label is not a collapsing massive star at all, but something else entirely, powered by a wholly different fire. For the core collapse events, the shape of the fading light tells the story of the envelope. The most common kind, type 2p, holds a plateau of almost constant brightness for about 100 days. During that plateau, the blast has ionized the huge hydrogen envelope, and a wave of recombination retreats slowly inward through it, as the hydrogen recaptures its electrons at a steady temperature, near 6,000 degrees. It releases the stored energy of the explosion at a nearly constant rate, propping the brightness up like a slow-burning fuse. Only when that recombination wave reaches the bottom of the envelope does the light finally drop, falling onto a long radioactive tail whose glow is powered by a different engine altogether, one buried in the freshly forged heart of the ejector. The proof of the whole picture arrived on the 23rd of February, 1987, when a star exploded in the Large Magellanic Cloud, a companion galaxy some 168,000 light-years away. It was the nearest supernova seen since 1604, and the first ever bright enough to study with modern instruments. On old photographic plates, astronomers found its progenitor, a blue supergiant called Sanduleak, the only star ever positively identified before it exploded. And then came the confirmation that turned theory into fact. About 3 hours before any telescope caught the brightening light, 3 underground detectors in Japan, in the United States, and in the Soviet Union recorded a burst of about 24 neutrinos spread over some 13 seconds. It was the first time humanity had ever caught neutrinos from beyond the solar system. Their number, their energies, and their timing matched with remarkable fidelity the prediction of a proto-neutron star cooling by neutrino emission. The core collapse paradigm had been caught in the act. Core collapse supernovae are the great forges of the middle of the periodic table. In their advanced burning and in the explosion itself, they synthesize most of the oxygen, neon, magnesium, silicon, sulfur, and calcium in the universe, along with much of the iron group, and then they hurl it all into space. As the outgoing shock momentarily heats the inner layers to billions of degrees, it drives a final spasm of explosive nucleosynthesis. Just outside the mass cut, the dividing line between what falls back onto the remnant and what is flung free, the shock-heated silicon and oxygen are cooked into iron group nuclei, and above all into radioactive nickel-56. That single, unstable isotope, created in the instant of the blast, becomes the power source that will light the supernova for months to come, long after the explosion's own heat has been lost to the expansion of the debris. The mechanism is radioactive decay. Nickel-56 is unstable, and it decays into cobalt-56, which in turn decays into stable iron-56, and at each step it emits gamma rays and particles that are absorbed by the surrounding ejector and irradiated as visible light. The rhythm of that decay is written directly onto the fading supernova. Nickel-56 has a half-life of only about 6 days, so it dominates the first couple of weeks. Then its daughter cobalt-56, with a half-life of about 77 days, takes over and produces the long, straight, exponential tail of the light curve, declining at almost exactly 1/100th of a magnitude per day. That precise slope, measured across supernova after supernova, matches the cobalt half-life measured in earthly laboratories, one of the cleanest fingerprints in all of astrophysics. And the final product, stable iron-56, is why iron is so abundant across the cosmos, and why it runs quite literally in our blood. Yet the heaviest elements of all cannot be built this way, because beyond iron, fusing nuclei together costs energy rather than releasing it. These are made instead by capturing neutrons. A slow process, operating over long ages inside evolved stars, builds many of them gently, but roughly half of everything heavier than iron, including gold, platinum, and the radioactive actinides, requires the rapid process, a furious flood of neutrons crashing onto nuclei faster than they can decay. For decades, the site of that rapid process was a mystery, with neutrino-driven winds from newborn neutron stars a leading suspect. Then, in 2017, astronomers watched 2 neutron stars spiral together and merge, seen both in gravitational waves and as a glowing kilonova whose light bore the unmistakable signatures of freshly minted heavy elements. Compact object mergers were confirmed as a major forge of the heaviest matter, though just how much they contribute compared with rare supernova remains an open and lively question. Now we return to that outsider, Type 1a, the supernova with no collapsing giant behind it. It is the complete thermonuclear detonation of a white dwarf, the cooling ember of a sun-like star, made of carbon and oxygen. Left alone, such a white dwarf would simply fade forever. But in a binary system it can gain mass, and as it is pushed toward the Chandrasekhar limit, the carbon at its center ignites. Because that matter is degenerate, its pressure barely responds to the sudden heat, so nothing expands to quench the fire. Instead, a thermonuclear runaway sweeps through the entire star in seconds, fusing much of it to nickel and iron, and releasing enough energy to blow the white dwarf completely apart, leaving nothing behind. These explosions make far more radioactive nickel than a core collapse event, up to 0.8 of a solar mass, and their spectra carry a telltale fingerprint of silicon. Whether the trigger is a white dwarf feeding on a normal companion or two white dwarfs merging is still genuinely debated, because a Type 1a springs from nearly the same trigger every time. A white dwarf reaching a critical mass, it reaches nearly the same peak brightness every time, for a few weeks rivaling an entire galaxy of ordinary stars. That makes these explosions superb standard candles. Compare how bright one truly is with how bright it appears, and you have measured its distance across billions of light years. They are not perfectly identical, but, in 1993, Mark Phillips found the key that made them precise. The brighter events fade more slowly, and by measuring how fast a supernova declines in the 15 days after its peak, one can read off its true luminosity and correct for the difference. That single relation sharpened these supernovae from rough estimators into rulers accurate to about 1/10 of a magnitude, precise enough to weigh the geometry of the cosmos itself, and weigh it they did with a result that stunned everyone. In 1998 and 99, two rival teams measured Type 1a supernova billions of light-years away and found them fainter, and so farther off than any decelerating universe could explain. The expansion of the universe is not slowing down under gravity, as everyone expected. It is speeding up. To drive that acceleration demands a strange component with negative pressure, which we call dark energy, and it appears to make up around 70% of everything there is. The discovery earned the Nobel Prize in 2011, and it has been confirmed by wholly independent measurements. Yet its nature remains one of the deepest mysteries in science. We do not know whether it is a constant energy of empty space, a changing field, or a sign that our theory of gravity is incomplete. That uncertainty now sharpens into the Hubble tension, a stubborn disagreement over exactly how fast the universe is expanding, which may be mere error, or maybe a crack through which new physics is leaking. Every supernova leaves a wreck behind it, the expanding remnant of shocked and glowing gas. Such a remnant evolves through well-understood phases. At first they eject a coast freely outward, then they sweep up enough surrounding gas to enter a long energy-conserving phase in which the blast wave grows as time to the 2/5 power and slowly decelerates, and at last they cool, pile into a dense shell, and dissolve back into the interstellar medium over hundreds of thousands of years. The canonical energy of the blast, about 10 to the 51st ergs, is so standard that physicists gave it its own unit, the foe. The most famous remnant of all is the Crab Nebula, the wreckage of a star seen to explode in the year 1054, a guest star recorded by Chinese astronomers that shone in broad daylight for weeks. At its heart spins the Crab pulsar, a neutron star turning 30 times every second, whipping out a wind of particles and magnetism that lights the whole nebula from radio waves to gamma rays. That central corpse is the second legacy of the death, and what it becomes depends on its weight. If the collapsing core stays below the maximum a neutron star can bear, somewhere near 2 and a fraction solar masses set by the still uncertain physics of ultra-dense matter, it settles into a neutron star. About 1.5 solar masses crushed into a ball only 10 or 12 kilometers across, often spinning and magnetized as a pulsar, but if the core is too heavy, no known force can stop it, and it collapses without limit into a stellar mass black hole, sometimes with barely any explosion at all, the star simply winking out in a failed supernova. Which giants leave neutron stars, which leave black holes, and which vanish quietly is mapped only imperfectly, tied to that same unsolved question of exactly how the explosion is launched. For all their violence, these deaths are also acts of creation on the grandest scale, the principal engines that shape whole galaxies through what astronomers call feedback. Chemically, each explosion seeds the surrounding gas with freshly forged elements so that every new generation of stars is born richer than the last, and Type 1a supernova in particular have supplied most of the galaxy's iron over cosmic time. Mechanically, each blast dumps its 10 to the 51st ergs of kinetic energy into the interstellar medium, driving turbulence, carving out great hot bubbles, and even blowing galactic winds that fling enriched gas far into space. Crucially, that heating disperses the dense clouds where stars form and so throttles the birth of new stars. Without it, simulations of galaxies catastrophically overproduce stars. And the shock fronts of the expanding remnants are the great accelerators of the galaxy, whipping charged particles up to enormous energies to become the cosmic rays that rain constantly upon the Earth. So the circle closes. The shock from a dying star, sweeping through space, can squeeze a nearby cloud of gas hard enough to make it collapse and give birth to new stars, so that death directly sparks life. There are hints, written in the isotopes of ancient meteorites, that just such a supernova may have helped trigger the collapse of the cloud that became our own solar system 4.5 billion years ago. It is a humbling thought to end on. The calcium in your bones, the iron in your blood, the oxygen filling your lungs, the carbon that frames every living thing, were all forged in the hearts of massive stars and blown across the galaxy by their explosions. We are not merely observers of these distant catastrophes. We are made of their ashes, stardust that has, for a little while, woken up and learned to look back at the sky.